This is ABC Fora.
When you look further out into space, you can see further back in time. And one of the challenges that faces modern astronomers is to try and investigate the geometry of the universe, perhaps 4 or 5 billion years ago, by looking at galaxies in very large numbers. And galaxies are huge aggregations of hundreds of billions of stars and dark matter and dust and gas and all the rest of it. But one of the things that we hope to achieve in the next decade is to probe the geometry of the universe perhaps 5 billion years ago, 4 or 5 billion years ago, which will give us a direct measurement of the springiness of the universe then, and allow exactly this question that you've raised to be addressed, whether it is now that the dark energy has become significant or whether it happened 4 or 5 billion years ago, which may actually give us some insight into what dark energy is, because at the moment we are really grasping at straws, I think is the fairest way to say.
We are. I mean, it's very interesting because I told you that we know that that there is the standard Big Bang theory. You know, I mean, we're pretty certain that the universe began in a hot, dense, compact phase, a fireball, and it expanded and has been cooling, and the galaxies have been congealing out of the cooling debris ever since. But in quite a few major ways, that standard picture contradicts what we actually observe. I mean, that picture predicts that the galaxies, which are kind of like pieces of cosmic shrapnel, they're under each other's mutual gravity, and so this expansion should be breaking, they should be slowing down. Yeah. And dark energy shows that that's not happening. They're speeding up. And there are other things like the standard picture of the Big Bang says that we aren't here. We cannot be here because
speak for yourself.
Because there hasn't been enough 13.7 billion years. There's not been enough time for the debris of the Big Bang to congeal or into under the force of gravity into galaxies like our Milky Way. So the standard picture predicts that we should not be here. What we do is we say, oh, there's a lot of missing stuff. You know, there's all this matter out there, and it's completely dark. We can't see it, but it's got gravity, and its gravity speeds everything up. And there's another more technical reason why the Big Bang doesn't work. So we have to tag on this kind of period of super fast inflation in the first split second of the universe. So all these things are bolted on in an ad hoc way onto the standard picture. So we have the Big Bang, doesn't work, so we tag on inflation. That doesn't work, so we tag on dark matter. That doesn't work, so we tack on dark energy. It's kind of a bit like the Greeks. You know, the Greeks were trying to explain the planetary orbits, and they really loved circles. Yes. You know, they really loved the idea of circles. Planets didn't seem to move in circles, so they thought, well, maybe they move in circles within circles, and then they move within circles within circles within circles. And they kept adding these epicycles on, and it turns out you can explain anything at all by adding epicycles. And of course, we now know that in fact the planets move in elliptical orbits. So it kind of feels a bit like that we keep tagging all these things on. But it feels as if there's a really, really big idea missing. You know, there's something missing in our picture of the universe. Someone in the next maybe 10, 15 years is going to come up with a missing idea, and it's all going to fit together in a much more logical fashion. So I have a real feeling that there's a revolution around the corner, you know, I mean, possibly of the kind of scale of quantum theory, you know, because, I mean, we can't really have our best physical theory, you know, predicting something and being wrong by, you know, 1 followed by 120 zeros. You know, that is really bad. The last time there was such a big discrepancy was in about 1910 and 1909, and that was when Ernest Rutherford, obviously a New Zealander, discovered the structure of the atom, and he discovered that there was this incredibly tiny nucleus at the center of an atom like a sun, and the electrons orbited around like planets. But the standard picture of physics said that those electrons should shed energy and spiral into the nucleus in 100 millionths of a second. Well, of course, we know that the atoms that we're made of, well, they certainly survived for our lifetime, and we think they've survived for billions of years. And that was a discrepancy between an observation and a prediction of 1 followed by 40 zeros. Yeah. And that led to a revolution. That led to quantum theory. The explanation of why electrons don't fall into nuclei requires quantum theory, which sees the building blocks of matter as kind of simultaneously you can't get your head around this, but they're simultaneously tiny little bullet-like particles, and they're also spread out waves, like waves on Sydney Harbour. And it's because waves are spread out things and they require elbow room, that the electrons in an atom require elbow room, and so they're actually, you know, atoms are relatively big and they don't fall into the nucleus.
It's astonishing.
Can't remember where
no,
I was answering.
It's all right. We were talking about the revolution that followed that giant discrepancy, and I'm really fascinated to hear you. First of all, having dismantled everything that all astrophysicists hold dear in terms of inflation and dark matter and dark energy.
And I'm a journalist, not a scientist.
But I do believe that it's a very interesting prospect to look at the idea that perhaps...
This is ABC Fora.